And now comes the time to prove a theorem that I have referenced a number of times, the so-called Isosceles triangle theorem, the ITT. It is an extraordinarily useful result. It will come up again and again throughout this class. And now that we have the SAS triangle congruence postulate, we are able with relative ease to prove the Isosceles triangle theorem. However, we'll have to move fairly slowly through this because uh, the initial move in this proof will be something different, something that we haven't seen so far. It will involve what we call construction. So first of all, let me define for you isosceles, which perhaps is a little different than what you thought it was. This is the modern definition, different from Euclid's, but it is the one that we will use. By definition, then, an isosceles triangle has at least two sides of equal length. Let me emphasize the at least two. Okay? One way to have at least two, of course, is to have two equal sides. Another way to have at least two is to have three. And we will come and talk about that in some more detail in just a moment, but do keep that in mind. Three is a possibility as well. Three equal sides does mean isosceles, as does two. Here's a little bit of terminology that describes, as it were, the anatomy of an isosceles triangle. The legs are a pair of equal sides. The base is the third side once we have chosen a pair of equal sides. The base angles lie opposite the legs. We'll talk about opposite in just a moment. It's a very simple spatial idea. And then finally, the vertex is the point of intersection of the legs. I know that one's a bit strange because really, of course, every triangle has three vertices, but in the context of isosceles triangles, we sometimes talk about the vertex, emphasis on the, and we mean the point of intersection of the legs. So in front of you, you see a triangle ABC with AB equal to AC as marked in the diagram. This means that we, of course, will choose AB and AC as the legs. Those are the sides that we know are equal. The base then will be the third side, which is BC, which doesn't have to come on the bottom, of course. It could be on the top or the side. Don't think that base means bottom. It doesn't. The base angles are the angles opposite the equal sides. And here's what we mean by that. So look at side AB, for instance. The angle that is opposite it, the one that lies on the opposite side of the triangle, is C. And the angle that is opposite AC is, of course, angle B. And then finally, the vertex, that is the point of intersection of the legs, is A. Now, do let me emphasize this, as I mentioned a moment ago, that equilateral triangles are indeed isosceles, and as a matter of fact, we can choose any two sides and call them the legs. So in the diagram that you see, yes, AB and AC could be the legs, or AB and BC, or AC and BC, and then once we have chosen our two legs, and we do have a choice, the base would be the third side. So for instance, if we chose BC and AC as the legs, then the base, of course, would be AC, which proves once again that the base doesn't have to be on the bottom, so don't think that it does. Now, here it is, the isosceles triangle theorem, the ITT. It says that in an isosceles triangle, the angles opposite the equal sides are themselves equal. So the given then would be this. We have a triangle ABC with a pair of equal sides, the legs, AB equals AC. And then we will prove that the measure of angle B is equal to the measure of angle C. So notice what the isosceles triangle theorem really does, what information it gives us. We know to begin that we have a pair of equal sides, and then what we are given is that we must also have a pair of equal angles. A side note here, many of the theorems throughout the class, throughout the entire year, involve relationships like this. They ultimately involve the relationships between side lengths of triangles and angle measures of triangles. And that's we have a wonderful example of that here. So the theorem says that if in a triangle we have a pair of sides of equal length, then we must also have a pair of angles of equal measure, namely the angles that lie opposite the equal sides. So as for how we prove this, I said at the start that the proof, though straightforward, does have a twist, a new kind of move in it. And that involves what I call a construction, what has always been called constructions in geometry. And for us, that will be in addition to the diagram. So we will take the diagram as given, the one that you see there, and we will make an addition to it, and that addition will be called a construction. Well, of course, we need rules about what additions we can make to diagrams. You imagine that that could go wrong, and that's will be a constant topic of discussion for us, how it is that constructions can go wrong. It's a subtle and difficult matter. they're not yet. So we will have rules that will tell us what we may construct. Well, where do these rules come from? They're ultimately all postulates or definitions that assert the existence of something or other. Let me give you a couple of examples here. Consider, for instance, the line existence postulate. It says for any pair of points, a line exists that passes through them. That is, if we start with a pair of points, then we are assured that a line exists that passes through them. And of course, we are assured as well that it is unique. Now, here's another one, the angle bisector theorem from back in chapter 3. It says for any angle, there exists a ray that bisects that angle. So once again, it assures us the existence of something given the existence of something else. So if we're given an angle, this theorem assures us of the existence of a ray that bisects that angle. Now, when we have existence postulates or theorems like this, then I think it makes good sense to, on the basis of that postulate or theorem, make an addition to the diagram. So for instance, if we had 2 points in a diagram, the line existence postulate would allow us to construct in, that is just to simply draw in the line. So here's an example. Let's say that in a diagram we had the points F and G, as you see them on the left-hand side, nothing drawn through them. The line existence postulate will allow us to draw the line that passes through them because, again, that postulate assures us of the existence of that particular line. Now, how will these moves appear in our proofs? Well, here's a suggestion. Let us make use of the constructions handout here. And then the names that are given to the constructions that we will use, we will put those into 3-column proofs. Okay, so you might take a moment to take a look at that constructions handout. You could pause and go to it on my website. You should also have a hard copy of that if you're a student in my class. And then the construction that we will need to use here is the C5 construction, one mentioned before, based on the angle bisector theorem. We will take an angle of our isosceles triangle and we will bisect it. That is, we will draw into our diagram a segment in that case that cuts the angle up into 2 equal subangles. So here it begins, the proof of the ITT. So notice that we have made an addition to the diagram. The original diagram was just the triangle ABC. We have now added to that the angle bisector AD. Okay, so notice line number 2. So it says construct angle bisector AD of triangle ABC. And that comes from line number 1, because which is the given, because the given tells us of the existence of the angle that we wish to bisect, that is angle BAC. And then it is that construction rule C5. Go take a look at your constructions handout again. Okay, it's the construction rule C5 that tells us that we may construct in that angle bisector. And then once that's been done, the rest of the proof is not particularly difficult. Okay, so we've constructed in the angle bisector, and then we are then told that angle BAD is equal to angle CAD. So let me go back and forth just a little bit. So angle BAD is equal to angle CAD. Oh, that follows from line number 2, which is where the angle bisector appeared, by the definition of bisector. And then we also know that AD is equal to AD. Oh, of course, that is just simply the reflexivity property. So how about REFL as an abbreviation for that? And that does come from the given because, oh, no, actually, this is another one of those cases where I wasn't careful. So let me be careful. From where does this come? Well, where is AD introduced into the proof? It's introduced by construction on line number 2. So we can go back and indicate that AD is equal to itself on the diagram. And then we say that triangle BAD is congruent to triangle CAD, and that's side angle side, okay? That's side angle side, and that's the only rule that we have at this moment in time that allows us to say that triangles are congruent. So let's see, what lines did we need to get to there? Well, we definitely needed line number 4, because that tells us that a side is equal to a side. We needed line number 3, that tells us that an angle is equal to an angle. And then we need the original given, because the original given also tells us that a side is equal to a side, namely that AB is equal to AC. Okay, so that is S. Ooh, I don't know how I did that. So that is SAS congruence. And again, here's an example where we have to make reference to 3 previous lines of the proof, which is for SAS congruence typical. because SAS congruence needs three equations to do its work, and very often those three equations are found on three previous lines. And then finally, we're able to conclude that angle B is equal to angle C. And notice that, yes, as a matter of fact, those are angles that correspond in our congruent triangles. B comes first, C comes first. So line number 6 follows from line number 5 by C, P, C, T, E. That is, corresponding parts of congruent triangles are equal. And with that, I'll say that we are done. We have now proven the isosceles triangle theorem. And let me assure you that you will be asked to prove this on the next exam from the start. You'll be expected to do everything yourself. It's an extraordinarily important theorem. You'll also be asked to prove it on the final exam for semester 1. And also on the homework assignment, you'll do a number of applications of the isosceles triangle theorem. And I walk you through that. So I think you should be able to do it. One very nice application is the equilateral triangle theorem, which says that the three angles of an equilateral triangle must all be equal. And you might think about for a moment how it is that that could be a consequence of the ITT